Hi there. Let's look at a few more examples of our change of variable substitution. So 3 examples, and let's see what we can come up with. So example A here, we have the indefinite integral of e to the square root of t over the square root of t dt. Yikes, this is kind of strange. But I think once we see what happens, it's not going to be a big deal at all. Now for these, I can say, oh, actually, no, for this first one, only I can say. So for this first one, I could say, hey, let the inside function be your choice for you, and that's probably going to work. But the last 2 examples, that's not going to work. So, the last video, picking the inside of the composite function usually worked, or it did work. And it'll work for this function, but the latter 2 examples, we'll have to try something else. But let's see what happens here. If we choose our substitution of the inside function, so let u equal square root of t, well, if we think that's our correct substitution, remember the immediate next step is to take the differential, find du. So du is, okay, we know the square root of t, the derivative is. Of course, we change it to t to the 1/2 power. We apply the power rule, and we get 1 over 2 square roots of t, and this is a differentiable, so we say dt. du is 1 over 2 square roots of t dt. Okay, well, notice what we can do now. We could say indefinite integral of e to the u, and watch if we separate this out, we could say times 1 over square root of t dt. Now, of course, it makes no sense to change, to have all these variables mixed in there like that. We need to change over to u completely. That being said, notice how we almost have the differential. We have a 1 over square root of t times dt. All we need is 1 over 2 square roots of t dt. So in other words, I need a 2 on the denominator, and then I can change that entire expression to du. Well, how do I get a 2 down there? I'm only missing a constant, and I know I can use the constant multiple rule to multiply by 2 over 2. But then, okay, I can pull in the 2 on the bottom and leave the 2 on the numerator out front. Leave a 2 there, and bring in the 2 on the bottom, and now notice what I have. This is exactly what I know du to be equal to. So I can replace it with du, which means now I have this new indefinite integral e to the u du, which is super easy to antidifferentiate, because we know the antiderivative of e to the u is just e to the u plus c. And then the last step, of course, is to back substitute to write this as e. Now we know u is the square root of t, so we write e to the square root of t plus c. Okay? Here let's double check, see if it works. Let's use differentiation. So the derivative, now this is with respect to t, of 2e to the square root of t. Okay? Now, just let's make a superficial change real fast. We can write that as t to the 1/2 power, since we're going to need to use the power rule. Okay, t to the 1/2 power. And the first step to differentiating this is to notice we can factor a 2 out. So 2 times the derivative with respect to t of e to t to the 1/2 power. Okay, well now we can do what? Well, we can apply the chain rule. So what's our outside function and what's our inside function? Well, according to the chain rule, the outside function is t to the 1/2. Sorry, that's the inside function. The outside function is e to the t, and the inside function is t to the 1/2. And what can you do? Well, the chain rule says, well, first of all, we leave that 2 up front. We have 2 times the derivative of the outside function is e to the t. But then we evaluate it at the inside function, so we replace the t with the t to the 1/2, and then we multiply by the derivative of the inside function, That's square root of t. And what's the derivative of square root of t? We know it's 1/2 times t to the negative 1/2 power. In other words, it's 1 over 2 square roots of t. And what do we get? The 2's divide out. E, t to the 1/2, that's e to the square root of t, divided by square root of t, which is exactly what we started with. So yeah, our antiderivative of 2e to the square root of t plus c is indeed correct. Awesome. Now, these last two examples, my general recommendation of letting the inside function be the substitution, well, it kind of fails. Why? Because these aren't necessarily, or they're not, I guess every function can be trivially composite, but these aren't really composite functions. Tan theta, like what is the outside, what's the inside? I mean, you could always write a trivial composition, but there's no meaningful composition for B or C. So what might we do? Well, B is actually a pretty standard derivative that you're going to come across sooner or later, and here we are. Watch what we can do. And this rang true a lot of times. When we did limits, a lot of times we would like to rewrite tangent in terms of sine and cosine. That wasn't necessarily true for derivatives because we know the derivative of tangent is secant squared. So we have to do that with derivatives. But here, I think it is advantageous to rewrite tangent as sine over cosine. So sine theta over cosine theta, d theta. Now, it's still not composite. It's still sine over cosine. That's just a quotient, not composite. But one tool that you need to keep in your toolbox, especially when you have quotients, is the fact that the antiderivative of 1 over x equals natural log absolute value of x plus c. What's more than that is, what if you have the composition, and remember how we took the derivative, let's say, of a natural log function, let's say natural log of u. Now, remember, if you apply the chain rule, what happens is you take the derivative of the outside function, which is natural log, and you write 1 over x. But you then evaluate at the inside function, which is u. So u is some function of x. So then you plug in your u, whatever that is, and then you multiply by the derivative of the inside function. But we're just doing this kind of abstractly, so what's the derivative of the inside function? We can call it u prime, maybe, or maybe du. In fact, du might be a good way to think about it now. So the derivative of u is so you have 1 over u times du, which I was about to rewrite, so I will now, as just du over u. So here's my point of this. Whenever you have the situation where the numerator is the derivative of the denominator, which that's exactly what's going on there, that is the derivative of the denominator. Whenever you have a quotient where the numerator is exactly the derivative of the denominator, you can always use natural log to anti-differentiate. And here's what I mean specifically. Now, you could do a change of variable. In fact, I will do that. What if we let the entire denominator cosine be u? Well, what would du be? Du would be what? Negative sine theta. Oh, I'm out of room. Need to scoot over a little bit. Du equals the derivative of cosine, negative sine theta d theta. So notice, if we let the denominator be u, then the numerator is almost exactly du. We have sine theta d theta. We just need negative sine theta d theta. Well, that's very easy to remedy, because what if I, imagine multiplying by, -1 twice. If you multiply by -1 twice, well, you can factor in one of those negative signs, because -1 is a constant, and put it there. So that just leaves us with negative out front, and then the numerator is negative, which is then du. And notice I now precisely have du over u, the derivative of the inside function over the inside function, which I know is equal to. Now remember, the only thing we have to worry about here is that, usually we would say, hey, there's the antiderivative right there, but we have to put a absolute value on the argument to make sure that the domains match. We talked about that in a prior video. That is one thing that's a little different about derivatives versus antiderivatives. Sorry, that's not an x, that's a u. We do natural log absolute value of u plus c. And now all we have to, sorry, there's a negative sign. I lost my negative sign. That was almost going to be a bad situation. Negative sign out front. Okay, and now we can back substitute, and we get negative natural log, what was u? U was cosine. So cosine theta, absolute value cosine theta, plus c. Cool. Let's check. So we're going to take the derivative with respect to theta of negative natural log absolute value cosine theta. Now, of course, we can factor out a negative sign. So let's do that. d theta natural log absolute value cosine theta. Now, we know that if we differentiate a natural log with an absolute value argument, it's actually the exact same thing as if we differentiate absolute value without the absolute value of the argument. So we can basically, I hate to say this, but we can ignore the absolute value in this case. The derivative is the exact same as if the absolute value is not there. So how do you take the derivative of a composite natural log? Well, we use the chain rule. We note the outside function is natural log x, or sorry, natural log theta. Natural log theta, and the inside function is cosine theta. And again, we're kind of ignoring the absolute value. So we get, of course, a negative out front. What's the derivative of natural log theta? It's 1 over theta. But then we evaluate at the inside function. So we plug in a cosine theta instead of a plain theta. And then we multiply by the derivative of the inside. What's the derivative of cosine? It's negative sine theta. Now, of course, we get a double negative, which leaves us with a positive sine theta over cosine theta, which is tan theta. Of course, tan theta being the original integrand. So our solution is indeed correct. Okay, cool. One last example for this video. Let's take a look. So we have the antiderivative, the indefinite integral of 8x plus 6 over 2x squared plus 3x dx. Okay. Now, here's what I'm noticing. Let's look at the denominator. Let u equal 2x squared plus 3x. I think this is going to work. Because, okay, if that substitution is going to work, well, then I need to calculate the differential. Now, the differential is what? That's 4x plus 3 dx. Now, I didn't mention this earlier when I was talking about differentials. If you have multiple terms in the derivative, then when you calculate a differential, make sure to put the derivative part in parentheses. So here we put 4x plus 3 in parentheses, then dx. Now notice how my numerator is curiously similar to 4x plus 3 dx, my differential. It's almost the same. Now it's not quite the same, but it is similar. Is there a way to make it the same? And let's see, what if we factor the numerator? What if we say this is equal to, if I factor a 2 out of the numerator, I get what? 4x plus 3 dx over 2x squared plus 3x. And then what is 2? So 2 doesn't need to be there. If I can get rid of that 2, then I have du exactly. And of course, 2 is a constant. I can factor it out, which leaves me with a numerator of 4x plus 3 dx over 2x squared plus 3x. And now my substitution takes care of this perfectly, because the denominator turns into a u, and my numerator turns into du, because that is exactly what du is equal to. And now I have that, I've erased it now. Now I have the classic du over u. Derivative of a function over that function is always going to use natural log. Again, u prime over u, or perhaps du over u, always has the antiderivative, natural log absolute value plus c. Okay? So here, simply antidifferentiate. Of course, there's a 2 out front. This is going to be 2 times natural log absolute value of u plus c. And then all I have to do is back substitute now. So I back substitute u, which is 2 times natural log absolute value 2x squared plus 3x plus c. Cool. Let's check it to make sure we're right. You know what? Let's leave that. I left that for all of those. We're just going to use the chain rule. So d dx, derivative with respect to x of what? Well, 2 natural log absolute value 2x squared plus 3x. I'm going to ignore the plus c. We have a constant multiple of a 2. Let's factor it out. That leaves us with a derivative of natural log absolute value of 2x squared plus 3x in absolute value. But remember, we can basically ignore the absolute value, because the derivative, whether there's absolute value there or not, is the same. So we could say this is 2. Now apply the chain rule. What's the outside function? Well, that's natural log x. Inside function is 2x squared plus 3x. So the chain rule says we take the derivative of the outside function, 1 over x. We evaluate it at the inside function, so we plug in 2x squared plus 3x, and then we multiply by the derivative of the inside function. And now the derivative of the inside function is what? 4x plus 3. And now I have a 2 times that term on the numerator. So if I distribute, I get 8x plus 6 over 2x squared plus 3x. And notice that indeed is my original integrand, so that is correct. Cool. 3 examples, 3 solutions, 3 verified solutions. All right, we'll take a look at 3 more examples. We'll wrap this section up in the next video with 3 more kind of tougher examples. They're fun though. All right, if you have any questions, always feel free to reach out. I'll catch you in the next video.